Good evening, everyone. I am Pragyan Shrestha from the University of Tsukuba. I'm going to present our paper titled Pose Estimation of Multiple X-ray Cameras Using Planar Markers and Epipolar Consistency. With the recent advancement of medical imaging technologies, intraoperative imaging is widely being utilized in many surgical operations. Minimally invasive surgeries, where small incisions are made for operations, as shown in the figure, and orthopedic surgeries for fracture reduction heavily rely on such technology. It is used mainly to compensate for the loss of visual information in the former and to confirm correct alignment and orientation of implants for the latter. Variety of modalities exist, such as X-rays, MRI, optical coherence tomography, and so on. X-ray is the preferred modality for orthopedic surgeries because it has high contrast for bone structures compared to soft tissues and ligaments. However, the problem with X-ray images is the loss of perception of depth. It is due to the transmission nature of X-rays, which follows from Beer-Lambert's law that states that the intensity decays exponentially along the ray path. Computed tomography scans can generate a high-contrast 3D image of bone structures. However, it is not practical to use it during surgery. Furthermore, a typical scanner would require a precisely circular imaging trajectory, which makes the device more costly. Cone beam CT is a technique to reconstruct 3D image from its 2D projections. It requires projection images and the corresponding pose information. The main challenge in cone beam CT remains to be the acquisition of pose information. A common approach is to adopt a C-arm mechanic, whereby the sensors attached to the rotating C-arm provide the corresponding pose information. This approach is prone to motion artifacts. A more flexible and cost-friendly approach would be to rotate the object and calculate pose information from the markers. Therefore, we propose a method of estimating pose information by identifying marker points in the X-ray image. The object is rotated with a calibration plane attached to it. From the acquired X-ray images, markers are tracked and correctly identified. The calculated extrinsic parameters are then optimized in two phases. The proposed method utilizes planar markers and epipolar consistency conditions. The calibration plane consists of 5 marker points as shown in the figure. The reason for adopting such method is because 1. Planar markers are easy to make. 2. The image-based approach eliminates the use of any external sensors, and furthermore, optimizing over epipolar consistency provides more accurate pose information. The epipolar consistency condition is based on Grandjeet's theorem. To explain it, consider a simple X-ray imaging system with an X-ray source and a detector. Here, f of r is the attenuation of the object. A ray from source to detector obeys Beer-Lambert's law. Therefore, a line integral along a line in detector would result in double integral over the attenuation. Now consider an epipolar geometry with 2 sources and 2 detectors. I0 and I1 are the corresponding epipolar lines here. One would expect that the line integrals along the 2 lines would be the same, since it amounts to the same plane integral. However, it is not the case in real because of the weighting factor introduced by the polar coordinate of the cone beam structure. Nonetheless, the derivative in the normal direction t would factor out the effect of the weight, and thus the following equation is obtained. In the original works of Eicher et al., the consistency metric was defined as the sum of squared difference of the derivative of the line integrals of corresponding epipolar lines. The parameter kappa is used to parameterize the pencil of epipolar planes. In this equation, Pi is the projection matrix of a reference view, P0 is a projection matrix of view being optimized. Using projective geometry, the corresponding epipolar lines can be calculated by multiplying transposed pseudo-inverse of the projection matrix and the normal vector. Our proposed consistency matrix constrains further by introducing reprojection error of the marker points as well. The reprojection error is the difference between the observed marker point and the reprojected marker point using estimated projection matrix. Our pipeline for pose estimation starts off by tracking the marker points in the image. A simple thresholding provides candidates for marker regions. A float fill algorithm is then applied to find the connected components in the image pixels. The centroid of each component is computed and considered as the marker points. The correspondence of these markers are then established by considering all 120 permutations and calculating the reprojection error from camera matrix obtained by decomposing homography in each case. The pose and correspondence with minimum reprojection error is considered as the correct one. Thereafter, the pose, namely rotation and translation, is further optimized using reprojection error of marker points in the given frame. The reference views are chosen such that it is separated by a given step angle beta. The step angle beta is computed as follows. Suppose that R and R' are the rotation matrices of two distinct views respectively. Rz and R'(z) are the third row of this matrix. We take the dot product and then apply R cosine to find out the angle between these two vectors and consider it as the step angle beta. The motion parameters consist of 6 degrees of freedom. T phi is the transformation matrix, which is right multiplied to the estimated projection matrix P0 to obtain the transformed projection matrix. The rotation is parameterized by Euler angles alpha, beta, and gamma. The translation is parameterized with 3 variables tx, ty, and tz. The problem then would be to minimize the cost function and find the argument for phi that minimizes the cost function. An experimental simulation environment was set up to test the proposed pose estimation scheme. The video on the left shows the simulated projection of a race phantom CT model. On the right, the ground truth and the estimated pose is shown. The camera axes are colored in RGB. Target rotation was simulated using HTC Vive Pro controller. The X-ray projection was simulated using Tiger, which is a framework for CT reconstruction in MATLAB. We can observe that the markers were tracked correctly for most of the views, and the mean reprojection error was 0.0195 pixels, which amounts to 0.004 millimeter, which is fairly low. However, we found out that some views have high error in terms of translation and rotation error before optimization. The figure in the right and the left shows translation error and rotation error respectively. The horizontal axis is the frame number of the video sequence and vertical axis is the error. The table in the right shows the error values for peaks of the figure. The translation error in these peak frames range from around 4 mm to 15 mm, which is significantly high. This is the same figure of rotation and translation error after our proposed epipolar optimization. Now the error values have lowered to around 1 mm to 3 mm. To illustrate what kind of correction was possible for the camera pose, this diagram shows the camera poses for two views that were optimized. The camera in red is the ground truth, the one in green is the camera pose before optimization, and the one in blue is the camera pose after optimization. You can observe that the translation in Z direction are corrected well, whereas there still remains error for the translation in Y direction. This is because we have used epipolar consistency condition, which cannot correct in-planar motion but can correct out-planar motions. Other points that we observe is that optimization over 6 degrees of freedom of the pose without the reprojection error term resulted in inaccurate local minima. This implies that the reprojection error term in the cost function is effective for 6 DOF optimization. To summarize, an image-based pose estimation framework using planar markers was proposed. The accuracy of pose estimation from planar markers degrade in some views. The proposed cost function was effective for optimizing over 6 degrees of freedom motion parameters. Thank you for listening.